Hello, this is Dr. Cleveland, and I am going to talk about t-tests in this short video. So the goals of the video are to explain a little bit about what t-tests do, what three aspects you need to decide when you're running a t-test, the type of test to use, whether or not you're going to do one tail or two, and selecting a p-value. And the third part is just interpreting the results both from the t-test table and the test output from Excel. So what does a t-test do? All right, it looks at the difference of means between two samples. And in this illustration, you can see here the blue and the red. It looks like they have different means. But a critical thing here is there's a difference in overlap. So we'll talk about that. The two populations overlap. If they didn't overlap at all, you're saying, oh yeah, it's pretty different. So that's pretty important. And then you want to determine if they're statistically significant. And very importantly, for a t-test, both samples must be interval measures. So they can't be the results from a Likert survey or, looking at, something nominal like different colors, because that's not directional. You have to have directionality and an interval measure, so you can't use a nominal or an ordinal. So where did this come from? Brilliant. Broad use was measuring the quality of stout back in 1908. A technician from the Guinness Brewing Company published a paper as student because the company wanted their techs, they gave their techs the ability to publish and take time to do research and publish, but they didn't want them to personally identify themselves, all in the name of good beer. Of course, if you know anything about the Guinness Company, they are also responsible for the Guinness Book of Records at first in the 1950s, mid-1950s, and now the Guinness Book of World Records. They went from looking at averages and difference of averages or means to the very farthest extremes. So, the types of t-tests. There's three different types. You have dependent samples and independent samples. With dependent samples, these are paired samples that have the same number of observations between the two different samples that you have. And what happens is you have a sample at different times, so before and after. So you have a group of individuals, you have some sort of intervention, then you have the same group of individuals afterwards. How did they perform on the same measure that you had before the intervention? You could also do test group and control group in match pairs design where the samples are equivalent on many measures and you might be just looking at one measure in difference. A/B testing is an example of this where, say you're running an advertisement, you want to see what the difference is between two advertisements. You change one specific thing about the advertisement and you see what kind of response you get. The other types of tests, independent samples with equal variation. So this means that you don't have to have the same number of observations in each sample for the independent samples, and the samples might not be, obviously they have to be related in somehow, because otherwise what's the point of comparing them, but it's not like the same individuals before and after. So you're just trying to say, how are they different? Expect that both samples are going to be similar in general characteristics, to have equal variation, and that means that you're not going to expect that there would be any change between the two groups in how the data is distributed across the sample, which is different from the independent samples with unequal variation. Is that you're really not sure. One can be really lumpy and have a lumpy data set, or one can be very equally distributed, and that's a really bad word to use, but one can be distributed pretty uniformly and very, say, close to everything is close to the means. You have a small standard deviation and the other one could have a really big standard deviation. These are the two different types of independent samples, and the unequal variation is slightly more conservative math, and they're two samples, and just to underline, they do not have to have the same number of observation between the two, unlike the dependent samples. So we figured out the one thing, the type of test. The second thing we have to figure out, one tail or two. And this is it's consequential. And it's important to understand what you're trying to accomplish with the test. Are you trying to say in the center is the two-tailed test, and you're just saying that they're different from the one-tailed test on either side here? On this side it says I'm greater than, and I'm looking for observations out in one tail of the distribution, or less than. I'm looking for, it's going to be a smaller. I'm looking for the left side of the distribution and saying, okay, this one is smaller than the other. In the two-tailed, you just say it's different. I don't really know which direction it's going to be, but it's different. So just want to talk now. So we've got the type of test, the number of tails, and now the p-value. You have to select the p-value. And just a normal distribution, you have the least likely observations out in the tails, and you have your most likely observations right here near the mean. And your p-value is, you set that to say, all right, at what level of probability will I accept that the observation that I have is not likely to have occurred by chance? So your p-value is often set at 0.05, which is 1 out of 20 times I'm going to see that. But sometimes, and not infrequently, it's set at 0.01 to say 1 out of 100 times I'm going to expect this to happen just by chance. So that's, pretty small numbers. And notice that the p-value here is set up by there's a value that you're going to have from a table, and that will correlate to the p-value. Okay, and I just want to visualize this again. So if you're out here, say at 2 standard deviations, you have 97.4% of the data is to the left side, so you have a very small chance that is to the right, and actually 1.96 standard deviations is where the p-value at 0.05 on a one-tailed test comes in, so it's right about here. So most of the data is to the left, and very little bit of the data is to the right, so that's pretty significant. And you're measuring how far these points are from the mean, and coming up with the standard deviation is going to be part of the calculation. So the math behind the test, this is really interesting math. I don't expect you to memorize all these, because actually you need to understand the concept, but memorizing the formula isn't super important because the computer's going to do the math for you. Now, a couple things. You've got an x bar, which is, and whenever you have the bar over the x, that means it's the average of the sample. So you have sample of 1 minus the sample of 2 is the numerator, and this generates how you can see if one is larger than the other, because if it's larger, then this value is going to be positive. It's if x2 is larger, so x1 is smaller than x2, the number is going to be negative. And that correlates with, okay, if I'm down at this tail, I'll be negative. If I'm up at this tail, I'll be positive. It just is which of the two means is greater than the other. Then you have your standard deviation in the bottom here, and the number of observations. Very important that the standard deviation, when you look at the spread of the data, if there's a big overlap between the two, this is where the standard deviation is going to be very critical in determining if the difference between the two is significant, because if there's a lot of overlap between the two populations, then it's a lot less likely that by chance you're going to see that the mean would actually have shown up by chance. So, and then the number of observations is also critically important. In fact, when the Guinness Beer folks developed this test, they were looking with small sample size numbers. So they wanted to include a sample size number in the equation, because the number of samples really makes a difference the number of observations in a sample makes a difference when you're looking at the normal curve, because it's the more observations you have, the more ability you have to describe the curve, rather than just, okay, there's 6 points, and is that really going to give you you're actually going to be able to visualize a curve? Maybe, maybe not. And then your degrees of freedom will be driven by your number of observations, typically just the total number of observations and then minus a single observation at the end, or depends on the number of tails that you have. We'll talk about that more in a moment. So this just shows you when you select 1 and 2 tailed test, one tailed test, all of the 5%, you say your p-value is 5%, all of your 5% is going to just go into one tail. So this changes the results, and we'll look at that in just a moment. And you're only 1.6 standard deviations away from the mean to get all that 5% in the one tail. On the two-tailed test, you split that 5% between the two tails. So you actually have to be almost 2 standard deviations away for the value to become statistically significant when you're just saying there's a difference. Remember, this is when you say one is bigger than the other or smaller than the other. This is when I'm not sure what the direction is, but they're different. So let's talk about results now, because we've covered how you select the test, 1 or 2 tails, the p-value. Now let's look at how the results. So say let me just skip back here to the equation. I actually calculated this t-value using this equation. Say I did that. I can go to a t-table and say, all right, I chose either the one-tailed test here in the top row and highlighted in red, or in green in the second row, the 2 tails. And you see that you have different columns because these columns will reflect whether or not you're going to take the 5% just all at once, or 2.5 and 2.5. And so you would go in the t-table and say, oh, I'm going to go over here, and then I would go down and say that we have a case where we've got 100 observations overall. My value is going to be 1.660 if I did the one-tailed test, but if the two-tailed test, it would be 1.984. And that would be your t critical value. So that would be the value here that you would set and say, all right, the t value that I calculated here has to be greater than this value, the absolute value, because if it's negative, it's still greater than the number. So it would be, all right, is it greater than, in this case, this is the standard deviations, but you can transfer that to a t-value when you do the calculation. So you would say, all right, what is the difference between these is the t-value I calculated greater than, more extreme than these t-values that I found here based on the degrees of freedom. And I chose 100 because I've got here a sample with male salaries, female salaries, 50 individuals in each sample, and I highlighted in this peach color. These are the 3 values that you would include in your test equation, and then what we have here, and to interpret the results, are the t-values in this kind of tealish color, and then in the light green we have the p-value. So the t statistic I calculated here, the t statistic I didn't calculate, actually Excel calculated it. Your t statistic is 1.94, and that is greater than 1.96, so that would be statistically significant for one tail. At 1.98 is greater than 1.94. So with the two-tailed test, this would not be statistically significant because the t statistic that I calculated is less than the critical two-tail from the table, right? So this is important, so that if I said that male salaries were larger than female salaries, and the mean suggests that they are, this would be significant only using the one-tailed test. It would not be significant just saying there's a difference and I don't know which direction it is. And this is also reinforced by the p-values. And the p-values with the t-test for one tail is 0.02. So at the 0.05 level, that will be statistically significant. But at the 0.05 level, this number is greater than 0.05. So this would not be statistically significant, because for the p-value, you want a number that's smaller than the p-value, which is different than with the table value, you want a value that's greater than your table value for the statistic. But for the p-value, you want a value that's smaller than the value that you set, the p-value that you set at 0.05. Now, I want to just also highlight the differences in the outputs from the 3 tests. Remember, we've got 3 tests, 2 samples including assuming equal variance, 2 samples assuming unequal variance, and then the paired test. And I did these 3 tests, even though it's not strictly appropriate, but I wanted to show you the difference using the same numbers, what the values are. So you have the degrees of freedom is 98 for the 2 sample assuming equal variance, and is 97 assuming unequal variance. That is the only difference, because for each one the mean is the same, the variance is the same, the numbers of observations is the same. The degrees of freedom is what's different when you select a test, and that's why it's important to select the correct test. Now in this case, the t statistic is exactly the same between the two, because you're looking up in the table and it's a two sample t-test, and the t-statistics, oh excuse me, this is not what you look up in the table, this is what you calculate. So what you calculate is going to be exactly the same. Now your p-values are exactly the same, up 0.0273, and then you get a 7.0273, and then you get a 9. So you see here that this number is a smaller number, for the equal is smaller than the unequal, so this is a slightly less conservative test than this, because you have the differences in degrees of freedom. So if you don't know that you have, if you're not very confident you have equal variances, safer to go with the unequal variances. And you see the same patterns with the t-critical values, the table values that you just select, slight differences here. So this is where, because it's the degrees of freedom, and 97 and 98 degrees of freedom, not going to be a massive difference, and you see that they're very close. And quite nicely, these also match the if you remember looking at this 1.660, 1.984, 1.660, 1.984. So thankfully we came out okay. There is bigger difference in the paired test. You only have 49 degrees of freedom, because you have the same individuals in each one, so you can't change the individuals that are in the test. You can only change that one test versus another, and you subtract that 1 degree of freedom. That, all right, once you define all the other, once you define that 49th variable, then that 50th variable has to be a given number, because it always has to add up to the same things, and we talked about this previously. So, and then you can see that there's slight differences in the calculations here. So that's all I got. I hope that this is helpful in understanding the t-tests. I hope you have a beautiful day.